All right, so again, we have a three-part definition of a limit. So we have our definition of a limit. The limit exists only when the two sides exist, the limit from the left and the right. That's our definition of a limit. A limit means you have limits from both sides. The definition of limits from both sides. Definition of continuity is these three parts. The point has to exist. So the point, there's a value there. It's not a hole. It's not an asymptote. It's not some weird situation. It actually does exist. So that's part number one. Number two, the limit exists as well. The limit from the left and the limit from the right are both the same. Part number two. That both these limits go to a single location. And the third part says the continuity happens when the limit and the function are both equal to each other and they connect. The point and the curve are all in the same location. That means we have continuity. If one of these three breaks down, you are not continuous. If you don't have f of c, if you don't have a limit, or if they're not equal, if one of these three breaks down, you don't have continuity. And that's how we mathematically define what continuity is. There's a point, there's a limit, and the limit and the point are the same. So let's take a look at some examples of how this can be applied. Say that I have a function f of x, and let's say they'd like to do this. Let's say that it is a piecewise function, and I have something like x squared plus x, and then 2x, let's see, plus hold on, I'm trying to figure this out. X plus something, plus 1. And let's say that this function, we have x, let's say this is 2x squared plus x plus 1. Say that. All right, here's our function. So the question is x continuous at x equals 1? This is our question. Is x continuous at x equals 1? How do we know? Well, we have to check our three pieces. We have to check, does a point, does f of c, c in this case is 1, does f of 1 exist? Do we have a location? And then we test our limit. Does our limit exist? From the left and from the right. And are they equal? 3 tests. So 1, check, 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 CK, f of 1. So we plug 1 into the function. Does it exist? So looking at this, we have a function that says x squared plus x plus 1 when x is less than or equal to 1. And it's this other one, 2x plus 1 when x is greater than 1. So which one do I plug into? Where is x equal to 1? Top equation or bottom equation? Which one of these would be the function existing? Yeah, top one, right? Here we have the equals to. Equals, this is saying that this is where it is equal to 1. So this is the top equation, we're going to get 1 there. So we're going to plug 1 in there. So f of 1 equals 1 squared plus 1 plus 1. That's going to be 3. So f of 1 exists. We're good. That's part 1. Check the function. Part 2, check the limit as x approaches 1 of f of x. Check the limit. So what do I have to do? I have two equations, right? I have a limit on one side, a limit on the other. I need to check to make sure my left and my right, because this is a piecewise function, I need to check it from the left, I need to check it from the right. So I'm going to check the limit as x approaches 1 from the left side. And which equation is it approaching on the left side? Well, it's less than, right? Left side is less than. Less than means I have this top equation. This is where all the x's are less than 1. So this is my left-sided limit. Okay? So the bottom function, we didn't use the bottom function for the first one to check because it's not equal to 1. Here it's equal to 1, here it's only bigger than 1. It doesn't actually reach 1 in the bottom equation, right? It's a limit. But we will be checking the bottom one for the limit on the right side. So this is the limit from the left side, we check the left equation. Limit from the right, we check the right equation. So the first limit, let's go back. It's, I'm running out of room here, zoom out. It's x squared plus x plus 1. So really what I'm doing is finding the limit as x approaches 1 from the left of x squared plus x plus 1. So I'm using the left side. So the left side equation, the negative part is the left side, that's the x squared equation. And to find a limit, this is just finding a limit. I chose this equation because it's the left side, but it's a limit like any other. To find a limit, I plug it in. So I'm going to get 1 squared plus 1 plus 1, and that's going to be 3. And that's the limit from the left. I now need to find the limit from the right. So I can say, right, this is my left, x approaching 1 from the left, and I can say this is the right, x approaching 1 from the right, because the greater than and because the less than. So x plus 1. So for this, I'm going to say the limit as x approaches 1 from the right side is 2x plus 1. We're using the 2x equation because that's what's on the right side, greater than 1. Right? If we're traveling like a little ant traveling from the right side, we're driving along, we're driving on that equation, on that line. That's the equation we're riding. Ride the line, everybody, ride the line. We're riding that line towards the limit. And as we get closer, right, same way we do for the other one, we find a limit by plugging in. If we can't plug in, we do other tricks, but this one we can plug in. So this is going to be 2 times 1 plus 1. which is 3. So my limits, remember we're finding the full limit, right? We're looking for the limit as a whole, right? We're looking for the limit as a whole. And so I have the limit from the left is 3, and the limit from the right is 3. So what does that mean for my limit as a whole? Limit as x approaches 1, the whole thing of f of x is going to equal 3. Because my limits match. The limit from the left equals the limit from the right, so we know they both go to the same place. So the full limit is the same thing as those other two. So my three-part definition of continuity, I'm checking if it's continuous. I check the value, I check the limit, and I check if they're the same. So part 3. Does f of 3 equal the limit as x approaches, 1, not 3. Does f of 1 equal the limit as x approaches 1 of f of x? Does the limit 3 equals 3? Yes, those two values match each other. So f of x is continuous at x equals 1. I said here 3 equals 3. I could have said f of 1 equals limit as x approaches 1. The limit as x approaches 1 of f of x equals f of 1. Check. We found the point, we found the limit, we found out if it's equal to each other, if they are continuous. All right, questions about this? Right, there are 3 parts. You have your equation, you look at what you're checking to see if it's at 1, so you check 3 things about 1. You check if the value exists, you check if the limit exists, and you check if they're the same. Let's do another example. Oh, green. Another example. Let's say f of x equals, let's do another piecewise function. Let's say it's x squared minus 5 when x is not equal to, let's say, 3, and x equals 2 when x does equal 3. So is f of x continuous at x equals 3? So we have a function, right? This first one here is saying that the equation is x squared minus 5 everywhere except for where x is 3. So this situation is like we have a graph, normal looking graph, except at 3, we take that graph away and we put a 2. So maybe the 2 is where we're supposed to do it in red. Maybe the 2 is where we're supposed to be. Or maybe the 2 is somewhere we're not supposed to be. Right? But this is how the function looks, right? We have this x squared equation everywhere except at 3, and at 3 I have this value of x equals 2. Is it here? Is it on the graph? How do I check, right? How do I check? So we're gonna do our testing. We're gonna check our 3 pieces. Whoops. Check if it's continuous, right? 1, does f of 3 exist? Does f of 3 exist? Yeah, well here. Here is where x is 3. When x is 3, it's a 2. We're equal to 2. What's the function when x is 3? X is 2. X is this value. I'm telling you what it's equal to at that. I should say, no, I'm sorry. I should say not 2. I should just say 2. Not equal to. It's just 2. At x equals 3, the value is 2. Yes. F of 3 equals 2. We're trying to test, does this 2 spot fill up the missing piece of this function at 3? So now we test the limit as x approaches 3 of f of x. Our value is 2. What's our limit? Well, we have one function. Do I need to test a left and a right? Do I need to worry about a split function here? Are we one equation on the left side and a different equation on the right side? What do you think? Do we need to worry about our left and right in this case? Are we split at all? It doesn't look like we're split. It looks like we're one equation. We just have this x squared minus 5, this one equation coming together. And we have like a blank, right? A blank at 3. We have this blank hole. But the limits are the same for both sides. It's the same equation on both sides. The limit going this way, the limit coming this way. So really what I'm doing is trying to find the limit of this function. Of the limit as x approaches 3. Limit of x squared minus 5. I just have my one equation. I don't need to worry, in this case, I don't need to worry about left and right because it's the same equation. It's not broken. I don't have a left and a right side. It's the same equation. So I just find the limit. What's my limit? X approaches 3 of x squared minus 5. Well, I find my limits by plugging in. So that's going to be 3 squared minus 5. 3 squared is 9. 9 minus 5 is 4. So my function is 2. The limit as x approaches 3 of f of x equals 4. Are these graphs continuous? Is this function continuous? No. Correct. Does f of 3 equal the limit as x approaches 3 of f of x? No. 2 does not equal 4. That's your answer. So f is not continuous at x equals 3. That entire sentence is your equation, is your answer. And you showed the steps, right? You showed the f, or the value, you showed the limit, you showed that they're not the same, and so it is not continuous. They don't match. So what we have is just like visually, just so you know visually what we have. Let me zoom out a little bit. What we have visually, the function looks like this, right? It goes up, but then if we wanted to, we wanted to be at 4, but the point, the filled in hole, was at 2 away from. Let me do that in black. The point we filled in was at 2 below where we wanted. So this is where it's not continuous. You see the function there, broken up. Oop. Okay, so the value, right, the equation looks like that. It goes up, and then it looks like it should be filled in at 4, right? We notice that the 4 is where we want to be, but the function puts this at 2. The equation says, well, at 3 you're going to be equal to 2. So we're not continuous. We have to jump there. Visually, that's what it looks like. The graph goes up, looks like it should be at 4. Right? If I asked you, and sometimes they do this, if I asked you the question, like, if I put here like a k, and I said, what should k equal to make the function continuous? If I asked, if there was a k, like a blank spot, if I said, what should k be equal so that this function is connected smoothly? Who has an idea? What should the point be? Where should I be to make this, to like fill this hole, to fill the space here? What should k equal? If I did want to make it continuous, if I had a blank there, where should I be to fill it? What should k be equal to fill that hole? To make it so this does connect, to put the bridge, to put the our bridge in there. What number should k be equal to? Right. Pariso says 4. Pariso is correct with 4. Yes. We're gonna equal the number that I want to fill in to connect it is equal to the limit, right? I said I found a limit. Well, if I know the limit, I know what I need to be equal to. Right? Here we found the limit. So I know if the limit's approaching 4, to make it continuous, I make it equal the limit. I make it equal 4. I know the limit's 4, so I make the point 4. K should equal the limit as x approaches 3 of f of x. To make it continuous. So k should equal 4. And that would fill in, that would imagine you fill in the hole, and you fill in the hole, and that smooths out our curve. It builds a bridge, right? You're building the bridge. You know where the bridge should be. You find the limit where the bridge should be. You fill in the hole, and that's where the bridge is going to be. Make that the spot. Okay? All right, one more example, and then I want you to try some questions. What if we have another kind of situation? So let me zoom back in regular. Another last example. Oh God. Another last example. What if f of x equals 1 over, let's say, x minus, why is this big word? X minus 2. Is f of x continuous at x equals 2? Paresh says no. Yeah, we know already from the situation, we know that we have what kind of situation here on the bottom. We have an x minus 2. What does that create for us? We know at 2, what's it going to be? Does f of 2 exist? Well, if I plug it in, it's going to be 1 over 2 minus 2, which is 1 over 0, so no. F of 2, even, like the point doesn't exist because we have a vertical asymptote, right? We have a vertical asymptote at x equals 2. So we can stop already. We know it doesn't exist. We know that it's not continuous at 2. But we have to, right? We have to say it, right? F is not continuous at x equals 2 because f of 2 does not exist. But just for completeness' sake, well, you know what? No, that'll be fine. So just so you're aware, like the graph, let's just look at the graph here. I just want to show you this graph. The graph of this would look like something like at 2, right? We would have this vertical asymptote. Our graph is going to go down like this and up like this. So if I were to say, there's an interesting thing that happens with limits in this situation that I want to tell you about. Let's just, for completeness, let's test the limit as x approaches 2 from the left and the limit as x approaches 2 from the right. What do these equal? Let's just take a look at this and explore this for a little bit. We know it's not continuous because we have an asymptote. But what do the limits equal? Is there a limit? The limit as x approaches 2 as a whole. Can we find a value for this limit? What can we say about these limits? Well, as we approach 2 from the left side, right here's, I'll do this in red, from the left side, what's happening to the graph? As we're approaching 2, we get smaller and smaller, more and more negative. And in fact, when we approach 2, this is an asymptote. Asymptotes go towards infinity. So this graph, as we approach 2, the limit, we can actually say this limit is equal to negative infinity because we go down. Down forever. So the limit from the left is negative infinity. And similarly, just from the right, we go up and up and up forever. We can say the limit from the right is equal to positive infinity because we go up. be green here. So from the left, we go down forever. From the right, we go up forever. But the limit as a whole, again, the limit from the left, if we're trying to find the limit from the left and the limit from the right have to be equal. Are they equal? The limit from the left is negative infinity. The limit from the right is positive infinity. Clearly, these two limits don't go to the same place. They go in totally opposite places. So we would say here the limit also does not exist. The limit also does not exist. And really, negative infinity is also not really existing because you don't ever actually reach, infinity is not really a number. So we would also say, we could also say DNE for these two as well. In all honesty, it doesn't exist. But in the AP Calc class, in the test, they will want you to say, oh, it's negative infinity because it's going down forever. Oh, it's positive infinity. But in reality, it doesn't exist. So the limit does not exist because the limit as x approaches 2 from the left does not equal the limit as x approaches 2 from the right. So the full limit, even that doesn't exist. Of f of x here and of f of x here. Okay? So that's a little bit more, hopefully, clarity on the limits and continuity and how we define it, right? These three pieces. You have to exist, the limit has to exist, and they have to equal each other. All those three pieces together have to connect. Whoops. Why was it a vertical asymptote? So there's a question, why is this a vertical asymptote at x equals 2? That's because when we divide by 0, when we plug in a 2, we got 2 minus 2, right? And we made a 0 on the denominator. And so our 0 on the denominator, we know when we have a 0 on the denominator and a number up on top, see it was a 1 on top, when we have that situation, we know it's a vertical asymptote. And if we wanted to check, like if we wanted to do our table, let me go over here, just like kind of a little aside for you. If we really wanted to, you could graph it and test, but if we wanted to make like a table of values as we approach 2, if you got really, really close, if you said like 1.999, you'd have a number that was like negative 700. And if you did 2.001, you'd have a number like positive 900. And so as you get closer and closer to 2, the numbers get smaller and smaller on the left and bigger on the right. And if you look at the graph, see the graph will be like that. But it's a vertical asymptote because it's 0 on the denominator, and it's negative here and positive there because we get closer and closer, they get bigger and bigger. Okay? Other questions? All right. So I'm going to stop this, and we're going to do some Khan Academy questions in these last 10 minutes. And we'll give those a try.